So please, George.
Thank you. Do I speak English or Georgian now? Misha, can you follow me in Georgian?
Yes, I can. Don't worry.
Wonderful. Misha იყო ჩემი კურსელი. რაც დიდი სიამოვნებაა და სიამაყე ჩემთვის, ახლა მე ინგლისურად ლაპარაკობ, ხოლმე ქართული სიტყვებით. მე ვიცი, რომ მიშა იყო აბსოლუტური მეფე თბილისის 22 მათემატიკური სკოლის. ამის მერე მიშა იყო პირველი ჩვენი კურსელებიდან, რომელმაც დაიცვა დისერტაცია. მიშა თავისი საუნივერსიტეტო შუა წლებში დაინტერესდა გრაფთა თეორიით. გრაფთა თეორიის არავითარი სპეციალისტები საქართველოში არ იყო. მიშამ ეს შეისწავლა თვითონ. სულ რამდენიმე წელიწადში გახდა საბჭოთა კავშირში ერთ-ერთი წამყვანი სპეციალისტი გრაფთა თეორიაში და ახალგაზრდებს ნუ გაგიგვირდებათ, რომ საბჭოთა კავშირს ვახსენებ, იმიტომ რომ მაშინ მართლა იზოლირებული ვიყავით და მიშამ დაამტკიცა, უпростоრად მოიყვანა გაუმჯობესებული დამტკიცება ამ ბრწყინვალე თეორემით, რომელსაც ხედავთ ეკრანზე და ეს არის ცხადია უბრალოდ ყველაზე მნიშვნელოვანი თეორემა ბრტყელ გრაფთა თეორიაში. დანარჩენს გვეტყვის მიშა და მადლობთ სასო.
Oh, thank you, Gogi. So I wonder, you can see the screen, right?
Yes, we can. Yes.
Yeah, I just brought up these old papers. There was I want to start with this kind of a controversy. The theorem about the planar graphs in the Western world is known to belong to Kazimir Kuratowski, and you see the paper, the original paper in French, where he's presenting this result, essentially classifying the planar graphs. The graphs are planar if they do not contain homeomorphs of two particular graphs that are presented here. You know, the complete graph on 5 points, and then the other configuration. There is a footnote. It is in French, but basically what it says is that Mr. Kuratowski learned from Mr. Alexandrov that the same result was presented a few years ago by Pantryagin, and Pantryagin never published the result. Pantryagin presented the result at the meeting of the Moscow Mathematical Society, like 2 or 3 years before publication of Kuratowski. And this is why I basically rediscovered a different proof of the same result. And this fact was also confirmed by Chogoshvili. I actually dedicated this paper to Chogoshvili, and he also told me that he apparently was present at the meeting of Moscow Mathematical Society when Pantryagin was presenting this result. So this is why I decided to name it after Pantryagin as well. So I called it Kuratowski-Pantryagin theorem. There is also a kind of an anecdotal fact that back in those days in the USSR, the universities had no authority to award the scientific degrees. Now, this result was included in my thesis for the Kandidat Nauk, but in those days, successful defense was not sufficient. It was necessary to get the certification from the certification committee, and the chairman for certification in those days in mathematics was Pantriagin. So after I defended the thesis, my thesis was certified within like a week. And this is primarily because I think Chogoshvili had sent a reprint of my proof to Pantriagin, whereas normally the certification was taking a few months. So that's basically the story behind the Kuratowski-Pantriagin theorem. But basically, what I wanted to start with is explaining why I got actually interested in graph planarity and what's the significance of that. So I actually created few. So basically, I already told you about the Kuratowski theorem. So why planarity is important? Planarity is important. It was important in those days when I was still in Tbilisi, because the industry in electronics was emerging, and even in Tbilisi there was an enterprise called Mion, where they were manufacturing so-called hybrid integrated circuits, and hybrid integrated circuits had a layer of polysilicon and a layer of metal. And if you take a piece of polysilicon and put a piece of metal over it, it becomes a transistor. That was discovered by American Nobel Prize winner Bill Shockley, who in the middle of last century founded a company called Fairchild, and they started developing the semiconductors and integrated circuits. Now, back in USSR, it was also followed, and the electronic schematics were usually, could be easily represented through graphs or hypergraphs, simply because the wires connect more than two contacts. So there could be hypergraphs, and the planarity was very important because, as I will show on the next screen, this is the typical, product. Basically, all the wires are laid out on a single metal, and it was important not only to find to determine that the circuit was planar, but actually to find a planar representation, planar embedding, and transform it into the geometries. And I was heavily involved in developing a software that was doing exactly this. And then on the next picture, there is basically a integrated circuit really manufactured at Mion. Mion was a facility in, I think it was in Digomi. That's where the plant was. And they were using the software that we developed, and the software was developed back in those days in Institute of Applied Mathematics at the university. That's the Beko Institute, and also in academy behind the sports arena, the computing center of the Academy of Sciences. Those were the two places that had computers in them, and there were not many computers in those days. But that was basically the practical implementation of the planarity concept and then the planarity algorithm. My proof of this theorem came from the fact that I was actually researching into efficient algorithms to find the embedding of graphs on the plane, and it just occurred that I discovered that when the polarity was not possible, the homeomorphs of these two graphs were always found. So when on the next slide, actually, I have my kind of a resume, which I just put together yesterday. And yes, indeed, I graduated from the 42nd school, the mathematical school in Tbilisi. I studied in
It was renamed Vekua School into the Vekua School much later.
Yeah,
so I also graduated from the same school.
Yeah. Well, in those days, Vekua was still well and alive. So it became Vekua School later. Then the university, I actually was in the Chagashvili's department, and official specialty was in topology and geometry, and that's where my thesis was classified into. But in reality, the focus of my thesis was in basically combinatorial theory and graph theory and graph colorings. So in '79, I emigrated to America. I was hoping to get to leverage the fact that I gained this experience in design of hybrid integrated circuits, and I applied for jobs just to get hired at several companies like General Electric, Texas Instruments, and so on. And I discovered a very interesting phenomenon, which was extremely frustrating to me. Yes, the engineering people wanted to hire me, but because I was from the USSR, I needed to get security clearance, and I was not getting it. The FBI was examining my case. They were talking to me on numerous occasions. They even asked me to take polygraph tests, which is the lie detector, because they accused me of being a Soviet spy. So I wasn't getting a security clearance, and I could not get a job at General Electric and several other companies until I applied to IBM, and they invited me for an interview and offered me a job in the T.J. Watson Research Center. And that was a very prestigious institution that was hiring only PhDs, and they had several Nobel Prize winners. And so it was basically, I felt very lucky that I got the job. And one of the facts that contributed to me getting the job was recommendation by Paul Erdős. Erdős was the Hungarian mathematician, very famous. There is a book out there about him, about My Brain is Open. I met him a few times in the past, and actually we had a article together, because Erdős was always inviting people that he had discussions with to become his co-authors. So later, you may have heard of, that among all the mathematicians, there is a graph where all mathematicians are nodes, vertices of the graph, and they're connected by, if they have a joint paper together. And then there is a concept of Erdős index, which means the distance in that graph from you to Erdős. Now, my Erdős index is 1.
So you published together with Erdős?
Right.
Okay.
So
Erdős number.
Erdős number. Right. So at IBM, I did primarily, I was focusing on the research in design of integrated circuits, even though it became apparent that my discoveries in planarity and efficient planarity algorithm became irrelevant because technology progressed and people started building circuits, integrated chips with 2 layers of metal. And when there are 2 layers of metal, one layer was dedicated to horizontal wires and another layer was dedicated to vertical wires, and there was no point in tonality, so it became irrelevant. So we call it an era of channel routing, and channel routing, basically, you have 2 layers of metal. The problem that needs to be solved becomes basically minimizing the width of the channel. And it is also can be formulated to some extent into a graph theoretical problem, where basically there are intervals, and if they're overlapping, intervals are nodes of the graph, and the intervals overlap, the nodes are connected. And then if that graph is colored, means in the graph coloring, you color nodes in different colors so that no 2 nodes of the same color are connected. Basically, if the intervals can be implemented on the same track, then they can be colored in the same color. So to minimize the number of tracks was to find a chromatic number of the corresponding graph. Now, graph coloring is so-called NP-complete problem, meaning that the optimal solution of this problem requires a non-polynomial complexity. So it's not practical. So it was important to find efficient heuristics for this problem. And that's what my focus became. I was researching into heuristics for channel routing, and I discovered and actually published while at IBM I don't have a paper right now, hierarchical channel router, which received the Best Paper Award in 1983. And later, I concluded that this can become a foundation of a differentiating technology. And in the year 1985, I decided to leave IBM and start a private enterprise to develop new routing technology based on the channel router. And the company was created. I actually moved to California. I was joined with 2 partners. One was from Poland. Another was my current partner, also from Tbilisi. His name is Boris Gruzman. He's about 5 years younger. So 3 of us, we started this company. We actually tried to raise venture capital. Nobody gave us any money. We talked to many famous investors, including Arthur Rock, who was a celebrity, and he was helping to fund the Fairchild Semiconductor.
So it was happening in Silicon Valley or where?
Yeah, in Silicon Valley. Yeah, actually, Arthur Rock was in San Francisco, on Montgomery Street. We visited him in his office, and he gave us an advice. He said that with what we're telling him, we don't need any venture capital. We should go and solicit development contracts from semiconductor manufacturers. And instead of getting hired, just develop this technology for them as contractors, and you will make it will become more practical. He couldn't see that it's inappropriate for venture capital investment, so we followed his advice, and we actually approached the Fairchild Semiconductor. Fairchild was very, as I said, was a very famous company, and the entire Silicon Valley actually has the origins in the Fairchild. The founders of the Fairchild were, besides Bill Shockley, there were Robert Noyce, Gordon Moore, Kleiner Perkins. They're all very famous people. Moore and Noyce were founders of Intel, and Kleiner and Perkins became very famous venture capitalists later. The name Fairchild came from an investor who was a very non-technical person, just, an investor who gave $3 million to fund the Fairchild. And the company later was worth billions of dollars, but then it spun off many famous startups and later disappeared. Basically, Fairchild was acquired by National Semiconductor in like in the 87. So what I'm presenting here on the right side is the first purchase order that my company, my company was called Descartes. The name was after René Descartes, inventor of the coordinate system. So this is how we called it. Our first order came from Fairchild, and later we learned that this was the last order of Fairchild. After giving us this purchase order, Fairchild was acquired and disappeared. There's no more Fairchild in Silicon Valley, but that was the first money that we received. We received 4 payments of $60,000, and we were able to hire several people, programmers, to develop the product. Then we got several other similar contracts from General Electric and a company called Silicon Compilers, but it all culminated in Japan, actually. The Japanese company Oki Electric had a subsidiary called Oki Semiconductor. They were designing a particular chip that they needed to become a little smaller. It couldn't fit into the frame that was desired. And I traveled to Japan. I spent like 6 weeks in Hachioji. It's a suburb of Tokyo. And at the end, I myself was basically executing my router and modifying it and tweaking it until the result was obtained. And in 6 weeks, Oki was able to complete the design, and they gave me a purchase order for $3.6 million. And there was also an article in Japan. I don't read in Japan, but somebody gave me a photograph of it. That was basically an article in Tokyo Shimbun in 1989 about this event. And essentially, Oki Semiconductor put us on the map. I returned to San Jose, and shortly one of our other clients proposed to merge with Descartes, because they were in themselves merging with a company called Mentor Graphics. Mentor Graphics was already $1 billion company and was offering, basically was acquired Silicon Compilers for $200 million. And Descartes' share was 10%. So that was the first real success. Later, of course, well, at least me, to some extent regretted that we sold the company, but in 89, it was the offer to receive, like $20 million was irresistible, and we sold.
I guess for many of us will be still irresistible these days.
Yeah.
For mathematicians.
Yeah. Then after we sold the company, I worked for Mentor Graphics for a couple of years. I was vice president of engineering, and but in '91, a significant event happened. That was the dissolution of the Soviet Union. And I felt that something should be done about it. I had many friends in USSR that I knew were extremely talented people, and I felt that if I can create a team of engineers and developers, there it could be of substantial interest. So I started a new company. We called it Gambit. Gambit is basically a chess opening, as you know, meaning material sacrifice for strategic advantage. But essentially, in '91, I actually practically moved to Moscow, and combined two teams. There were two organizations that were heavily involved in the past in design of electronic circuitry, the NITSEFT, and then the facility in Zelenograd, which was the precursor of the neon plant, and I had connections there. So I put together a very powerful team, and we developed basically new technology for design of integrated circuits that became quite popular. I relocated the team in '93 to San Jose, at least part of it, but the remainder of the team was in Moscow. And in '99, we sold the company to Synopsys. Synopsys was and still is a leading company in electronics design automation, and it was basically a very interesting deal for us, where we basically received $50 million and moved the rest of the team from Moscow. Synopsys is located in Mountain View, so that's where the rest of the team is. Most of the team that came from Russia to Synopsys is still employed and works for Synopsys.
Excuse me, what is EDA?
EDA stands for Electronics Design Automation.
Mm-hmm, mm-hmm.
You see, the chips, where the electronic circuitry is implemented, they are extremely complicated. They have millions of transistors and millions of wires. Somebody has to lay them out. So they're laid out by algorithms. It's computers that, and we were developing these algorithms. This is what we did. It's impossible to think that the design can be implemented by humans because of the sheer numbers, and the window frames, because of the competitiveness of the chip design processes, that you usually have like few weeks to complete the chip design and actually go into manufacturing. So EDA is very essential, tools, and basically it's a whole industry which is a derivative industry to semiconductor industry. EDA tools are very expensive. Typical license is like few $1 million, and they are very essential. They're basically the core technology in microelectronics production. Later in 2001, I actually started a different company, decided to leave Synopsys. Together with my partner, Boris, we started a company called Golden Gate Technology, which we operated from until 2007. The company ultimately failed. The promise of Golden Gate and the reason we started was we were under the impression that we can design the chips to minimize chips power consumption. Power consumption of a chip now is extremely important, and had we started that company maybe 10 years later, we would have been a lot more successful. But in 2001, we envisioned that power consumption will become important, but it was a little premature. Well, we discovered that it was premature only later. This company, Golden Gate, because we were already having such a successful record in the past, we raised a lot of money from venture capitalists. Me and Boris, we actually invested some $6 million of our own money and raised another 30 million from marquee VC funds. We developed new technology, but it basically the differentiation was that if we could differentiate the wires by switching activity, if we can simulate the circuit and know which wires are switching more than the others, we could make those wires shorter. You see, the power consumption of a chip is basically, power is consumed because of the switching wires, and the power consumption is proportional to the capacitance of the wire, which is proportional to the length of the wire. And if the high switching wires were made shorter at the expense of low switching wires that could be longer, then the chip will consume less power. That statement is true, but the savings in power consumption in those days were very small. We could only save maybe 5%. And Intel bought one copy of our tool. Nobody else bought anything. So the enterprise essentially failed. I ended up repurchasing 10 patents. I was actually one of the authors of most of those patents. I think I'm on the list of 9 out of these 10, but Golden Gate received 10 patents, but only 2 of these patents ended up being useful. So the company dissolved. I owned the patents. I ended up monetizing the patents 5-6 years later. All my former employers, Synopsys, Mentor Graphics, and then there's another company called Cadence, they used basically the patented ideas, and they all agreed to license those patents from me. So I actually recovered some money by licensing those patents to these companies. But I myself was not looking to get another job after failure of Golden Gate. Instead, I became what they call an angel investor. I was fascinated by the works of venture capitalists in general, but then, and I was considering to join a venture capital fund and was in discussions with a couple of funds, but then ended up not joining. My friend, who is a venture capitalist, was explaining to me that yes, venture capital is very glamorous. On one hand, you can fund successful company and you meet very talented people, but in reality, 9 out of 10 venture capital investments fail. Only maybe 1 out of 10 succeeds. And most of the time in the life of a venture capitalist is spent by trying to recover failed investments. So they are, if they are lucky to invest in a company like, next Bill Gates and next Steve Jobs, they have very little opportunity to interact with Bill Gates or Steve Jobs. They just go by themselves. Instead, they spend time, trying to recover or help the failing companies, and that's not very interesting activity. So I did not join any of the venture capital funds. I basically became a private angel investor, and I invested in several companies. And this is my score sheet. I had invested in a company called Trend Software, doing business as Property Minder, and then another company called Media Boost. They are completely in different areas. Trend Property Minder basically is focusing on tools and websites for real estate industry, and Media Boost is a company essentially is an advertising agency automating placement of advertising for small businesses. I later put these two companies together. They're still active. Then I had several failed investments in a company called SciCAD that was EDA on the cloud that failed. My 6 Sense, Israeli company that was basically also in advertising space, also failed. Vector Fabrics in Netherlands. Another investment I made in Sage. Sage basically was an Israeli company also in the EDA space, and it was successfully sold to Applied Materials a couple of years ago, and I realized basically a 10x return, so which helped me recover the failed investments. And my final slide, my current occupation. I am still operating this company, Trend Software. We operate with 2 trademarks, trade names, Property Minder and Media Boost. The companies are involved in automating of advertising on social media. It's very different, of course, has nothing to do with electronics design automation, but it addresses the fact that social media is a new phenomenon. It's a new modern phenomenon where people are spending a lot of time, and they are very popular. Obviously, you heard of Facebook and LinkedIn and Instagram and Twitter. All these companies, they provide services to their users for free. They make money by advertising, by selling advertising. Small businesses pay Facebook and Instagram and Twitter, and they show their advertising. Small businesses need to advertise, and we basically help automate the advertising process. We create advertising content and optimize between social media platforms. It is a very promising business, but I'm basically running it. I'm chairman of the board, and I'm running the engineering group still. We have 25 employees here in San Jose. We have 28 employees in Novosibirsk in Russia. Again, we inherited this. I did not start this company. I was just an investor, but I ended up getting involved in running it because the founders of the company, they left. And so we transformed the company. And ever since I got involved in this group with Novosibirsk, it's a powerful team, very good people. I was dreaming to maybe move them to Georgia, because simply, traveling to Georgia is a lot more pleasant and desirable for me than traveling to Siberia. So, but we never did. We were just dreaming about it. However, due to events of the past 2 weeks happening in Russia and Ukraine, we decided to make a move. And we made a decision that, yes, we will be moving to Georgia. I already engaged the law firm to start a company. We have decided to open an office in Batumi. There was a big discussion here where to start the first office, in Tbilisi or in Batumi. And My wife is from Batumi, so the discussion was primarily with my wife, and she prevailed. So we'll probably end up having offices both in Tbilisi and in Batumi, but we'll be moving there. We'll probably move a couple of people sometime maybe in April or May. We know that due to this events happening in Russia, there is quite a crowd of people moving now, to Georgia included. But that's...
Oh, this is the answer to Mamuka's question he asked in the beginning.
Yeah. Yeah. So we will be hiring actively in Georgia as well, because we will not move all people. We will end up probably moving maybe 10 employees, because people have families, they have connections. They will not everybody will be able to move, and we don't need all 28. We can easily find comparable talent in Georgia. So that's the idea, and that's what I will be involved with in the next few months. So that's pretty much all I wanted to was ready to tell. So if you have any questions,
George is the chair, supposed to be the chair of this session. Yeah.
All right, thank you. Please, questions or comments? So I don't think I will be a good chair because I cannot see things like raised hands.
I mean, we can speak
may
up.
I ask you to be the chair?
Okay, you just see Mamuka's. Okay, Mamuka, please.
Well, I'm Mamuka. I have some question, if it's possible.
You should raise hand.
So Mamuka was first.
Raise hand. I don't even know. I'm not that familiar with Zoom. We use here a different platform for this meeting, so I also cannot see any raised.
Okay, Mamuka, I can see hands, so I will be, calling.
But actually, Sasha is older than me, so
Okay.
I give him.
So let me stop recording if you don't mind.
Thank you, Mamuka. Misha, first of all,